Hi everyone, this is Mrs. GA, and today we're going to learn how to graph polar equations. Okay, so we're going to start with some really basic polar equations, and we're going to sketch a graph on our polar axis. So the first equation is r equals 3. So this is essentially saying all of the times when the distance of the point is exactly 3 units from the center of our axis. So that would just be all of the points around the third ring. So our graph actually just makes a circle. So it looks just like this. So anytime you just see r equals a number, it's going to be a circle centered around the origin. Okay, now let's try theta equals pi over 3. So this is saying all of the points whose second value of the coordinate theta is pi over 3, which is 60 degrees. So it'd be everything along this line. So these are for when you have positive r values, but of course you could also have negative r values. So it actually covers everything on this continuing line. So it actually looks more like a linear equation. Okay, so now we're going to try graphing one that's a little bit more complex, and we can do this by making a t-chart. So we can pick some values for theta and then see what the values for r become. So let's do some in the first quadrant to see what we get. We'll do 0, 30, 60, and 90. So we know the sign of 0 is 0, so this will be 0. The sine of 30 degrees is 1/2, and times 2 gives you a value of 1. The sine of 60 degrees is root 3 over 2, times 2 gives you just root 3. And then the sine of 90 is 1 times 2 is 2. So let's plot those points and see what we get. I'm actually going to change the scale of the graph, the scale of the polar axis. Maybe instead of counting by ones, imagine that I'm counting by halves. So here's 1/2, here's 1, 3/2, 2. So go ahead and change that when you take these notes. So 0, 0 gives us a coordinate right here. 30 degrees, 1 gives us a point right here. Remember, I changed the scale of the graph. 60 degrees gives us root 3, which is a little bit less than 2. So it'd be right around here. And then 90 degrees gives us 2. Okay, so let's plot some more points and see what we get. So if we do 120, we get the same thing here. We get root 3. For 150, we get 1, and then for 180, it brings us back to 0. So here, a little bit less than 2. At 150, we get 1, and then 180 is 0. Now, if you keep plugging in angles that are in quadrant 3 and 4, you'll see that you're just going to get these same exact coordinates over again. Yeah, the angles are down here, but you're going to get negative r values, which bring you back to the same points. So we can actually just sketch a graph from here. So it actually does make a circle, kind of like r equals a value. However, you'll notice that this circle has been shifted up. So it actually has a center that is shifted up 1. So this is the center of our circle rather than being centered on the origin. Another thing to note is the diameter of this circle is 2, so it's probably not a coincidence that this value is also a 2. Okay, go ahead and pause the video and see if you can sketch a graph of this equation by making a table of values. And we'll check your answer in just a moment. Okay, so here's my table of values, and again, I changed the scale of the graph to be counting by half for each ring. So my scale is by every half a unit. So here's my values. So for 0, we get -1, so that actually brings me over here. Remember, 0 degrees is here, but we had -1 in the opposite direction. 30 degrees, negative root 3 over 2 is actually here. So again, since your r value is negative, you have to travel in the opposite direction, and root 3 over 2 is a little bit less than 1. And then we have 60 degrees, but -1/2, so here, 90 degrees, 0. And then we have 120 degrees, 1/2, 150 root 3 over 2, and 181, which brings you back to where you started. If you kept going, your points would just be in the same exact spot. So here you can see that we have another circle. Again, this circle you can see has been shifted over. So now this one has been shifted over to the left. And notice that the diameter of the circle is 1. Okay, so one thing that might help us when we are graphing that can save us some time is using symmetry. So any graph that has sine of theta will be symmetric about the line theta equals pi over 2. So if you have values that are in quadrant 1 and quadrant 4, you can simply reflect them over this line rather than having to plot or make more points in your table of values. So that can be really helpful. And then for any graph involving cosine, it's always going to be symmetric across the polar axis, our horizontal axis. So that means if we have graphed values that maybe are in quadrants 1 and 2, then we can reflect them to graph values that are down here, or vice versa, depending on where our points fall. Okay, so using that new fact, let's see if we can sketch a graph of 2 plus 2 cosine of theta, and we'll see if we can save ourselves time by reflecting our values. Okay, so when I'm picking angles for this equation, since the equation is a little bit more complex, maybe I'm going to pick some nicer values for cosine. So I'll do 0, and then I'll do 60 degrees, and then we'll do 90. And then we can do 120 and 180 to see what we get. Okay, so here the cosine of 0 is 1, times 2 is 2, plus 2 is 4. For the next one, this is why I picked 60, because the cosine of 60 degrees is 1/2, times 2 is 1, plus 2 is 3. The cosine of 90 degrees is 0, so this just becomes 2. The cosine of 120 is negative 1/2, so this value, or this expression, becomes negative 1. 2 minus 1 is 1. And then the cosine of 180 is negative 1, times 2 is negative 2, so 2 plus negative 2 is 0. So let's plot those points and see what our graph starts to look like. So we have 0 degrees 4, 60 degrees 3, 90 degrees 2, 120 degrees 1, and then 180 degrees 0. And then since it is a cosine graph, I know that it is symmetric over our polar axis, so we can simply reflect all of these to the other side. So 121 would reflect down to here for 240. And then I can also plot a point at 272 and then 303. So now if you connect these points, we get something that looks like this. And there you have it. So this is actually a really common shape for a graph. There are a few different really common polar graphs that we're actually going to be talking about on the next slide that we can kind of use to help guide us more graphing as well. So if you know to expect a shape like this based on the equation, it can make your job a little bit easier. Okay, so here are some of those common polar curves that I just mentioned. So the first row talks about how you can make spirals and circles. So that first example we did where it was just r equals some number creates a circle that's centered on your polar axis. And then if you have r equals a sine of theta, you have a circle that has been shifted up or down so it's on your vertical axis. And then if you remember, we kind of alluded to the fact that the diameter of your circle was that a value. And then for cosine, it does make a circle as well, except this time it's shifted horizontally along your polar axis. And again, this value is a, the diameter. So notice again, this is a sine graph, so it's reflected over the line theta equals pi over 2. This is cosine, so it's reflected over your polar axis. And then if you have a graph that is simply r equals a times theta, notice there's no sine or cosine. It actually makes a spiral shape, and you can plot some points to give you an idea of how fast that spiral is expanding. Okay, the next category of graphs are called limicons. So these are 4 different types of limicons, and the equations come in the form of a plus or minus b sine theta, or a plus or minus b cosine of theta. So between the sine and cosine, it just it determines how it's reflected. So these would all be examples of sine graphs. But then you'll notice that there's these extra features. So we have this inner loop, and here it comes to a point, here it's dimpled, and here it's convex. We determine those extra features based on comparing the a and b values. So here, if our a value is ever less than our b value, we're going to get a limicon with an inner loop. So again, if that a value is ever less than your b value. And the plus or minus has nothing to do with the b value. Think of the b value as always being positive, as it states here. Same for the a value. Now, if your a and b values are exactly the same, we get a pointed limicon, which is called a cardioid because it is kind of heart-shaped. So that's the one we just graphed on the last slide. If your a value is ever greater than your b value, we get a dimpled limicon. So you can see that it still comes in. It's still a little bit concave, but it doesn't come to a distinct point like your cardioid. And then if your a value is more than twice your b value, or exactly twice your b value, you actually get a convex limicon. So it's no longer concave, it's more convex. Okay, the next category of graphs are called roses. So they come in these 2 forms. So a times the sine of n theta, a times the cosine of n theta. So here you can see we have multiple angle equations. So again, you need to see if it's sine or cosine to see how it's reflected. But also the key thing here is to look at that n value. So it's a little bit an interesting pattern, but if that n value is odd, it tells you the exact number of petals or leaves to expect on your rose curve. So for example, here n is 3 and we have exactly 3. Here n is 5 and we have 5 petals. Now if your n value is even, we have twice as many petals. So here our n value is 2 and we end up with 4 petals. Here our n value is 4 and we end up with 8 petals. So you have to know the rule for when n is odd and when n is even. Another thing that might be useful when we're graphing, the length of our petal is always going to be a, whatever this a value is. And then it's also really useful to note that your petals are always going to be evenly spaced about your axis. So if you know where one petal is and you know how many to expect, you can just split 360 degrees up into the number of petals and you'll know exactly where to graph them. So that can save you a ton of time when you are graphing. Okay, the last category of some common polar curves you might see are called lemniscates. So they're these like figure 8 shaped curves. They kind of look like infinity symbols. So these are the 2 forms that you might see. So they're really a dead giveaway because here we have r squared and then we have equals a squared times the sine of 2 theta. So notice for both of these it's 2 theta, which is why we have the 2 kind of petal shapes here. But one thing to note is for the sine graph, it's always exactly opposite along the line, along the angle pi over 4 or 45 degrees. And then for cosine, it's always reflected right over your polar axis. One more useful fact here is the length of your petal is a. So note that this value is going to be a squared. So the length of this petal is going to be the square root of this value. So if you know what the equations, what types of curves they create, it can really help save you a lot of time when you're graphing. You still will need to do a small table of values, but it really helps like when you have something like an inner loop or maybe a dimple, so you'll know what to expect in your graph. Okay, so let's have a look at this next example and let's see if we can use what we learned on the last slide to help save us some time and give us more direction when we're graphing. So looking at this, we can see that this is going to be a rose curve. So that's one thing we know about it. So remember, if this n value is odd, it tells you how many petals to get. So we're going to have 3 petals exactly. We know that the length of the petal is going to be 5 units. And then we know that since it is a sine graph, it's going to reflect over your vertical axis. So we can use that to help us. So essentially, all we need to do is figure out where our first petal is, and then we could find the other two by placing them evenly around our axis. So let's start by making a t-chart with just a couple values. We can try doing 0. So here, the sign of 0, 3 times 0 is 0, is 0 times 5 is 0. We can try 30 degrees. So this is actually would be the sign of 90 degrees, which is 1 times 5 is 1. And then let's do 60 degrees. So if it's a sign of 3 times 60, it's actually the sign of 180, which is also going to be 0. So then that brings us back to 0. So if you plot those points, we see that we start here. 30 degrees brings us out to 5, which we know would be the tip of a petal, and then 60 degrees brings us back to 0. So we would actually get a petal that looks kind of like this. Try one more time. Here we go. And again, I know this is the tip of my petal because of this A value. It tells us the length. So now that we know where one petal is, we know that the other two, again, are going to be evenly spaced. So we take 360 degrees and we split it up into 3 parts for the 3 petals. So we know that they're going to occur every 120 degrees. So we start at 130 and we add 120 to that, and so we'll have another petal at 150. So again, it's going to be 5 units out, and it's going to have that same shape like this. And then we're going to add another 120 to that, bringing us to 270. So that's where our third petal will be, and it will look like this. So by using what we know about common polar graphs, it can save us a ton of time, and we know exactly what to expect from this equation. Okay, let's try this next example. So here we have 1 minus 2 times the sine of theta. Okay, so based on the form of this equation, we know that this is going to be a limison. And because our A value is less than our B value, remember the negative is separate, so we're just comparing 1 and 2. We know that it's going to have an inner loop. And because it is a sine graph, it's going to reflect over our vertical axis, so that can save us some time. And then we'll see later on in our graph if we can figure out what we think this negative actually did. What would a negative do compared to a positive? So again, let's make a t-chart. We'll do some values and see where that leads us. So again, if we have any points here, we can simply reflect them on the other side, and same thing here, we can reflect them. So let's start with just some basic ones. So we'll do some nicer values for sine. So let's start with 0, 30 degrees, and 90. So sine of 0 is 0, times 2 is 0, so this just gives us 1. The sine of 30 degrees is 1/2, times 2 is 1, so 1 minus 1 is 0. And then the sine of 90 is 1, so here this gives us 2. 1 minus 2 is -1. So let's plot those points and see what we get. So here's 0. I'm going to change the scale again. So imagine the scale of our rings is by every 1/2, just to make it a little bit easier for me to plot it. So for 0 degrees, it brings us to 1. For 30 degrees, it brings us to 0. And then for 90 degrees, it brings us to -1. So we're actually going to go in the negative direction, like this. Now, because we know this is a sine graph and it's reflected over our vertical axis, we can also plot a point right here. We can reflect that. But we definitely need some more points. So I'm actually going to pick some values from down here in quadrant 4 to see what that gives us. So down here in quadrant 4, let's do 270, 330, and then we can go back to 360. So the sign of 270 is -1, so times 2 would be -2. So this is actually 1 plus 2, which gives us 3. We know that the sign of 330 is -1/2, so this gives us -1, so 1 minus -1 is 2. And then here again, the sign of 360 is just 0, so this just brings us back to 1. So let's try plotting those points and see what that gives us. So remember, I scaled it by each ring is 1/2 of a unit. So for 270, I have to go 3 units, so 1, 2, 3. And then for 330, we are 2 units out, so 1, 2, and then 330 brings us back to 0. And then I can reflect this point over our vertical axis as well to give us an additional point. So here is where it's really useful to know what to expect from our graph. So since I know that it's a limison with an inner loop, I'm saying how can I connect these points in a way to make that happen. So in my head, I know that it should look something like this, or maybe it could be flipped upside down. So it's something like this. So we can see that with the points that we have, it will probably be a flipped upside down limison, and we have to again connect it so it has that inner loop. So we can kind of do a graph that looks like this. And there you have it. So again, we could do some extra additional points to give us a little bit better idea, but at the end of the day, it really, really helps to be able to look at the form of the equation to tell what type of curve to expect. And maybe here notice that we can generalize that when this is a negative, so when our sine portion is negative, that we have kind of an upside down graph rather than an upright graph like this first example. Okay, let's try another one together. So again here, by looking at this graph, I see it's one of those multiple angle graphs, and so this must be a rose curve. Since the end value is even, I know I'm actually going to have twice as many petals, so I'm going to have 4 petals. And I know the length of each petal is going to be 6 units. And then again, I know that it's going to be reflected over the polar axis because it is cosine. So we really just need to figure out where one of our petals is, and then we can sketch the rest just by spacing it out evenly about our polar axis. So here, let's start with the table of values for just a couple angles. Let's just try 0 degrees, 30 degrees, and 45 degrees. So we know that the cosine of 0 is 1 times 6 is 6. So since it's going out 6 units, we can infer that that actually would be the tip of one of our petals. So that's nice. We've already located it. Let's get a couple more points just for accuracy. So the cosine of 2 times 30 is the cosine of 60, which is 1/2. So 1/2 times 6 is 3. And the cosine of 2 times 45 is the cosine of 90, which is 0. So here we have 3 coordinates we can plot. So 0 degrees 6, 30 degrees 3, and 45 degrees 0. Since this is a cosine graph, I know that I can reflect over my polar axis, so I actually also have a coordinate here. So you can see this is one of our petals. And again, the rest of our petals can be placed by dividing the rest of our space evenly amongst the 4 petals. So we know that if we have 360 degrees and we're splitting it up for 4 petals, it's going to be 90 degrees apart. And of course, we're always going to do this from the very center of the petal. So if I start at 0 and then I go 90 degrees, that means I have and I go 90, I have another petal at 90 that has a length of 6. So we can kind of draw another petal like that. And again, this is just a rough sketch. We could find more exact coordinates if we needed to. And then I go 90 degrees from here, and I end up at 180. So we can go right to here. Here's our third petal. And then we go 90 degrees from there, leaving us at 270. So here's our last petal. And there you go. All the petals should look the same, so you can use those extra points again to help make them a little bit more accurate. But again, just knowing what to expect from this equation can save us a ton of time, and it can help us make a much more accurate graph. Okay, let's try this next one together. So here, again, based on the form of this equation, we are going to have a limison. And here, since our A value is larger than our B value, but it's not twice as large yet, we are going to have a dimpled limison. And since it is a cosine graph, we know that it's going to reflect over the polar axis. So anything that's on the top, we could reflect to the bottom or vice versa. All right, so let's start by finding a few coordinates and seeing what that gives us. So we can start with, we'll start with 0, 60, and 90 to see what we get. So the cosine of 0 is 1, times 2 is 2, 3 minus 2 is 1. Here the cosine of 60 is 1/2, times 2 is 1, 3 minus 1 is 2. And the cosine of 90 degrees is 0, so that just leaves us with 3. Okay, let's plot these coordinates to see what we get. So here, let's start with 0 degrees 1, which is right here, and then we have 60 degrees 2, and then 90 degrees 3. And then based on the fact that it's a cosine graph, we know that we can reflect it over our polar axis. So we can reflect this point on 60 degrees to 300 degrees, and we can reflect 93 to 273. Okay, so now we need to find a couple more points over here. So let's do 120, and we'll do 180. So the cosine of 120 would be negative 1/2. So this gives us -1, 3 minus -1 is positive 4. And the cosine of 180 is -1. So this gives us -2, 3 minus -2 is 5. So here we can plot those points, 124, which I can reflect down to here. And then we have 185. So based on what we know to expect from an equation like this, a dimpled limison, we can see that we can just connect our curve to look something like this. So again, it is dimpled, which means it is concave. It comes in a little bit, but it doesn't come to a point like that cardioid shape. So we have something that looks like this. Okay, let's try this last example together. So here, based on the form of the equation, we know this is that lemniscate, kind of that infinity-shaped graph. And we know that because it's sine, it's going to be reflected over the origin on 45 degrees and 225 degrees. And then we know that the length of the petal, or the length of, I guess, the leaf, is 2, because remember this value is a squared. We do have exactly 2 petals. So we can actually just go straight to 45 degrees and plot a point at 2, so right here. And then we have our point right in the middle. And then we can go down 225, and we can go 2 units out that way. And we actually end up having a graph that looks like this. There you go. So again, this one is really useful to know what shape this makes, and it can be a super, super quick sketch. Again, things to watch out for. This is a squared, so the length should be 2, and since it's sine, this is where it's going to be. If it were cosine, it would be along your polar axis. Okay, so that is all for today's video. Thank you so much for watching.